Hey everyone, welcome back to Real Analysis 1. This will be lecture 7 of the course. And in this section, we're going to continue with our investigation of sequences and limits of sequences. And specifically, we're going to introduce the idea of a subsequence. And alongside the concept of a subsequence is the very famous Bolzano-Weierstrass theorem, which we'll get into as well. All right, so let's go ahead and get started. We'll call this section 2.4, Subsequences and the Bolzano-Weierstrass theorem. Okay, so this I'd say the main idea of this section will be the Bolzano-Weierstrass theorem. Subsequences play into that. They feed into a number of theorems that are required to prove the Bolzano-Weierstrass theorem. So let's go ahead and get started with that. We'll get going with the concept of a subsequence first. So let's define a subsequence. Okay, so given a sequence, and we'll denote it just using P sub n in R. These are real numbers, of course. Given a sequence P sub n in R, let's consider a sequence n sub k, where k is equal to 1 to infinity here, of positive integers, so these are natural numbers. I'll say natural numbers. Okay. Consider a sequence n sub k of natural numbers such that n sub 1 is less than n sub 2, which is less than dot dot dot, which is less than n sub k, which is less than dot dot dot, right? So basically increasing sequence. Okay. Then the sequence P sub n sub k, okay, P sub n sub k, where k is equal to 1 to infinity, is called a subsequence. It's called a subsequence of P sub n. Okay, so kind of a wordy sort of it's kind of a wordy definition, but the idea of a subsequence is very it's simple. It's basically you have a sequence, then you consider some subset of the sequence that's defined by the indices, right? So you've got this sequence n sub k, where it's strictly increasing, and you use that as your index on your original sequence, and that is how you define the subsequence. Okay, so we'll do some examples in a second. It's not as tricky of an idea as maybe it seems, but what we'll see here is that if P sub n sub k, this is the subsequence, if it converges to a limit, then the limit it converges to is called the subsequential limit. So if the subsequence converges to a limit, then the limit is called a subsequential limit, right? So just kind of an extension of the definition. Okay, so you've got subsequences, and they may have limits, and if they do have limits, we can qualify them as subsequential limits, meaning they're the limits of some subsequence. Let's see some examples of a subsequence. Okay, we'll start with some kind of simple, easy to visualize examples. Let's consider the sequence 1 minus negative 1 to the nth power. I think we've seen this one before. Right, so this is we'll think of this as the P sub n. This is the main sequence. And we could consider just the even terms of the sequence, right? The terms where n is even. So if n is even, then a sub n is what? Well, whenever n is even, you've got 1 minus 1, right? So whenever n is even, a sub n is equal to 0. And if n is odd, well, in that case, you've got 1 minus negative 1, so 1 plus 1. In that case, n is 2. Okay, right? So this sequence really just has two options. It's either 0 or it's 2, depending on whether or not n is even or odd. And so 0 and 2 are subsequential limits of this sequence. Okay, so kind of a nice simple example to look at. Another one's kind of similar, but maybe we'll explore this one with a little more depth. Let's consider negative 1 to the nth power plus 1 over n. Okay. Now let's think again about the even and odd subsequences. So if n is even, then we'll say n is equal to 2k. Okay, so this would be the kind of the way to index it. So then a sub n would be equal to a sub 2k, which would mean that the term of this, the kth term of the sequence would be negative 1 to the 2k power plus 1 over 2k. Okay, and this is going to converge to 1, right? Right, you can see what would happen here is the limit as k goes to infinity of negative 1 to the 2k plus 1 over 2k. Well, the first term of the sum is going to go to 1, right? These are all basically going to be equal to 1. It's always even. So negative 1 squared, negative 1 to the 4th, negative 1 to the 6th, etc. And so this is going to be equal to 1, and then what's going to happen to this other piece? Well, the denominator is going to grow without bound, and so that means this is going to go to 0. All right, so the limit here is 1. Okay. So a sub 2k goes to 1 as k goes to infinity. Now what about the odd terms of the sequence? The odd terms of the sequence, so when n is odd, then a sub n would be equal to, there's different ways to write it. Let's just write 2k plus 1. Okay, and so that would mean that the kth term is negative 1 to the 2k plus 1 power plus 1 over 2k plus 1. Now what happens to this limit? Okay, so the limit of this is what? Well, again, here, this is basically a constant. It's always going to be equal to negative 1. Negative 1 raised to an odd power is negative 1. So you get negative 1, and then this similarly, this is going to go to 0. Okay, so you've got two subsequential limits here. You've got 1 and negative 1. Okay. Now it turns out that's all that there is in the case of this one. This is an oscillating sequence. All right, so something important to note here is that while we do see subsequential limits in these two examples do not converge in general. Okay, so these two examples do not converge in general, right? So the second one, I guess, the last one we looked at, it was negative 1 to the n plus 1 over n does not converge. And then the other one was, let's see, I think it's 1 minus negative 1 to the n, I think. This does not converge either. But we did see that there did exist subsequences of these two sequences where we did have convergence. Okay, so let's think about kind of the reverse of that, all of that setup, right? So what if we have a sequence that does converge? Does it imply something about the subsequences? And the answer is yes, and that's going to be our first theorem. Okay, so let's let P sub n be a sequence in R. Let's let P sub n be a sequence in R if P sub n converges to P. If it converges to P, then every subsequence of P sub n also will converge to P. Okay. So if you have a sequence that converges, automatically every subsequence converges, and automatically every subsequence converges to the same limit. Okay. Now this one is very easy to prove, and I think this isn't terribly difficult to believe. Really, this is not, I think if you think about it for a second and you really understand the idea of what a subsequence is, I think this is pretty intuitive. This is not something that you would have this shouldn't be shocking. Okay, let's go ahead and prove this theorem quick. So let's let P sub n sub k be a subsequence of our main sequence P sub n. Okay, and then let's let epsilon greater than 0 be given. Okay, so we know by assumption P sub n converges to P as n goes to infinity, right? And so that fact implies that there exists some natural number n naught. Okay, and there's going to exist some natural number n naught such that P sub n is in the epsilon neighborhood of P for all n greater than or equal to this n naught natural number. Okay, that's just the definition of convergence of a sequence. P sub n converges to P by assumption, which means there exists a natural number such that once you get out beyond that natural number, you're within epsilon of the limit. Okay, and now let's bring in the subsequence concept. Now, since n sub k is strictly increasing, right? Remember that n sub 1 is less than n sub 2, which is less than ... right? Right, that's kind of how we defined a subsequence, right? The indices have to be increasing, which means we just basically have to be moving forward in the sequence. Our subsequence is going to include terms that are gathered by subsequently moving forward. Okay. So since n sub k is strictly increasing, n sub k is greater than or equal to n sub 0 for all k greater than n sub 0. Okay, and so what does that imply? Right, and so therefore, what does that imply? Well, what it implies is that P sub n sub k is in the epsilon neighborhood of P for all k greater than or equal to n naught. Right, and that's just the definition of convergence. So P sub n sub k must go to P as k goes to infinity. Right, which means, that's another way of saying that the subsequence P sub n sub k converges to the same limit as the main sequence. Okay, so just applying the definitions here, basically just using the straight definition of convergence here. All right, very good. Very good. Let's look at an example. Okay, let's consider an example. Let's consider p sub n, or not p sub n, p to the nth power, okay, where p is between 0 and 1. Okay. We saw previously, right, we've looked at this one 2 lectures back, I believe. We've seen that this sequence, p to the nth power, is monotone decreasing. It's monotone decreasing, and it's bounded below. It's bounded below. And given the fact that it's a monotone function and it's bounded, it must converge. Therefore, it must converge. Okay, so this guy must converge. We know that it must converge. Let's assume that a is equal to the limit as n goes to infinity of p to the nth power. Okay. Now, by the previous theorem, every subsequence of this sequence must also converge, and it must also converge to the same value. So what that means for us is that p to the 2n must also converge. Okay, if we take every other term, it must also converge to the same value, right? It must also converge to a. And so what can we do? Well, we can say then that a is equal to the limit as n goes to infinity of p to the 2n, right? And we know that that's the same as the limit as n goes to infinity of p raised to the nth power squared, right? And so that must be a squared. Okay. And so, I mean, this is a great example of how you can just kind of use this theorem to force some kind of an algebraic setup that allows you to kind of figure out what the limit is, right? So a is equal to a squared, and if a is necessarily between 0 and 1, well, remember p is less than 1, right? So if a is equal to a squared and a is between 0 and 1, it could be 0, then obviously a equals 0, right? And so p to the nth power goes to 0 as n goes to infinity, right? So it allows you to kind of reason about what the limit must be using the fact that the subsequence must converge to the same value. So it's a nice little example. Okay, now in order to, so that's the first piece that we need for the Bolzano-Weierstrass theorem from this lecture. The second thing that we need to know, that we need to define, is the concept of a limit point. Okay, so this is a very nice little idea that will get used a lot in analysis, but will specifically require it for the Bolzano-Weierstrass theorem. So let's define this. This is the definition of a limit point. Let's let E be a subset of R. Subset of the real numbers. Then you've got two options here. The first option is a point P in R is a limit point. It's a limit point of E, right? So limit points are defined in relation to a set, right? So a point P in R is a limit point of this subset of RE if every epsilon neighborhood we would denote that n sub e p, n sub epsilon p. If every epsilon neighborhood of p contains a point q, which is in E, with specifically q not equal to p. Okay, so a point P is a limit point of a set if every epsilon neighborhood, no matter how close I get to P, there's going to be some point that's not P that's in the subset E that's in that epsilon neighborhood, no matter how close I get, right? So the idea is every epsilon neighborhood, right? So that means epsilon can be infinitesimally small, and even if it's infinitesimally small, I can still find a q that's right next to p that isn't equal to p, that's in the set E, right? If that's the case, then we say that p is a limit point, right? It's a limit point. It's a point where the values that are in the set E are infinitely dense, right? They're right next to each other. Okay, now there are lots of points that aren't limit points, and if that's the case, right, if P is not a limit point, if it's not a limit point of E, then it is and we say isolated point. It's an isolated point of E. All right, so you're either a limit point or you're an isolated point. All right, now that's the idea of a limit point. And we'll frequently refer to limit points as accumulation points also. So limit points are also called accumulation points. Right, accumulation points. Or I've even heard points of accumulation. I think limit points is probably the one we'll use the most. Okay. Now, notice that the definition does not require that the limit point be in the set E. Okay, so note P does not need to be in E in order to be a limit point. Okay, so P does not need to be in E in order to be a limit point. But frequently it is. And in the case of E being, or of P being in E, well, let me just write this out here. But it frequently is. And if it is, then we can characterize limit points. So if it is, we can characterize limit points in a different way, right? Right, and we can use kind of the idea of an intersection, right? So if your limit point, or if your point of interest is in E, then P in E is isolated. It's isolated if there exists an epsilon greater than 0 such that the epsilon neighborhood of your point of interest intersection with E is equal to just P. Okay, so that's kind of another way to think about it. We don't really define it in this way because, again, limit points don't have to be in E. But if the point you're trying to think about, if you've got a point in E and you're trying to determine if it's a limit point, this is a characterization that's frequently useful to say, well, can I find an epsilon greater than 0 such that the intersection of my epsilon neighborhood in E just contains P? If so, then it can't be a limit point. And so a limit point would require that for all epsilon greater than 0, the intersection is going to contain something else. Okay. Okay. Let's look at an example here. Let's take a look at an example. Examples are king. So let's consider kind of a straightforward example here, something that's not tricky for us. So consider this sequence n equals 1 to infinity. Now we know that 1 over n goes to 0 as n goes to infinity. And from this you could probably guess that 0 is a limit point. 0 is a limit point of e if we set e equal to all of the terms of this sequence. Right, so if we let e be all the terms of this sequence, then 0 is a limit point of e. Now notice that 0 is not in e. Right? 0 is not in e. E is going to contain only non-zero rational numbers. Right? So 1 over 1, 1 over 2, 1 over 3. It's going to get very, very close to 0 as n gets very, very large. But 0 is not in e, but yet 0 is a limit point of e. Okay. Now what about the other points what about the other points that are in e? Are any of them limit points? So are any of the points in e limit points? Well, it turns out that the answer to that is no. None of the other points in e are limit points. There's just the one. So there are no limit points in e. 0 is a limit point of e, but it's not in e. Now let's think about what this thing looks like if we were to draw this out. So 1 over 1 is 1, right? So you've got this guy over here, and then on the other side you've got 0, which is not in e. Right? So I'm going to put a blank there. Right, but then you've got 1/2 is the next one, and then you've got 1/3 and 1/4, right? And they just kind of start piling up down here. Okay, so you can imagine. Now, just to kind of help illustrate the idea of a limit point, let's think about why the number 1 here is not a limit point. Right, so the idea is that can I construct an epsilon neighborhood about this point 1 such that 1 is the only thing in the epsilon neighborhood from e? And the answer is yes. I could let epsilon equal 1/6, for example. Right, and so that would be, so this would be 1 minus 1/6, and this would be 1 plus 1/6, so 7/6 up here, right? And so this would be, the whole thing would be my epsilon neighborhood about 1. Now the only element from e that's in this epsilon neighborhood is 1 itself, right? So the epsilon neighborhood of 1 that I've chosen here, epsilon equal to 1/6, contains just, well, that neighborhood intersecting e contains just 1. Sorry. Okay. And so for that reason, it's isolated in e. Right? Now, this same idea could be done for every point in e, right? So if I want to think about 1/2, I could easily come up with an interval around 1/2 that just contains 1/2. And I could easily come up with an interval around 1/3 that just contains 1/3, and so on, right? There's no difference as I get closer and closer to 0. The only thing that happens is my epsilon neighborhood gets smaller and smaller, but it's always possible for me to construct such an epsilon neighborhood. Right? And for that reason, just the fact that they get very, very close together is not enough, right? They do get closer and closer together, but there are these gaps between them, which makes them isolated. Okay. Okay, so all of the points in E are isolated points of E. 0 is the only limit point, and 0 is not in E. Okay, very good. Let's take a look at another example here. Examples are so important in math classes. You really have to see lots of examples. Let's take a look at this example. Let's let E equal the interval a to b, where a is less than b. Right. So here we've just got an arbitrary open interval a to b. Now, what happens in the case of an interval like this of real numbers, right? So this is of real numbers. Okay, so an open interval on R. So every point that's between A and B, every point P between A and B is a limit point of this set. Okay, so every point P between A and B is a limit point of E. Right, and this is just because, look, we're talking about all real numbers, you know, greater than A and smaller than B. And we know that the properties of the real numbers provide that, right, so this would follow. This follows from the fact that for any epsilon greater than 0, there's going to exist an x in AB such that P is less than x, which is less than P plus epsilon, right? There's always a number between two numbers in the real numbers, right? So you can't, it's not possible, this is an uncountable interval. It's not possible to find, you know, two numbers that doesn't have another number between them, right? And that's the basic idea here. Okay, and so I've got A and I've got B. Here's my P of interest. You know, obviously if I just have P minus epsilon here, P plus epsilon, there's going to be some X here. Right? That's all that you need. Right? No matter how small the epsilon neighborhood gets, I can always find some number X that's inside of it that isn't P. Now it turns out also that A and B, the endpoints, are not in E, but they are limit points of E. Okay, so A and B are also limit points of E, but note A and B are not in E, right? Because it's an open interval. Okay, it's an open interval. All right. Very, very good. Very, very good. So kind of a key idea here. Let's do one more example. We just want to make sure we have good intuition about this limit point idea. Let's let E equal the intersection of the rational numbers and 0 and 1. So basically this is just the rational numbers between 0 and 1. Okay, so we can denote it like this, right? So the rational numbers between 0 and 1. Okay. Now, if P is not in this interval, it turns out, if P is not in the interval 0 to 1, then it turns out that P is not a limit point of E. Okay. And we can kind of see this. Let's go ahead and consider let's consider a case here. Let's let P be greater than 1, right? So P is, we're considering a point that's larger than 1, so it's outside this interval. Okay, it could be right next door. It could be very close to 1, maybe 1.00000000001 or something like that, but it's outside of the interval. Okay, so if p is greater than 1, how can we show that it can't be a limit point? Well, we could say for epsilon equal to 1/2 of p minus 1, then the epsilon neighborhood of p intersect E would be empty. Okay, let's draw this. Let's see what this looks like. Okay, so I've got my number line here. Here's my upper edge. There's my 1. And so that is in E. And then I've got some other number that's a little further up. And this is the P of interest. Okay, and so I can construct an epsilon neighborhood around this thing, right? Specifically, whatever P happens to be, I can set epsilon equal to 1/2 P minus 1. Okay, so this would be P plus 1/2 P minus 1. And this guy down here would be P minus 1/2 P minus 1. Okay, and it turns out that there is no, these bounds are basically established so that no matter how close P is to 1, this is going to be right in between, and it's not going to intersect E at all, right? So there can't be any rational number. As soon as you cross that line of 1, then you've got dense rational numbers everywhere. But outside of that, I can easily construct a neighborhood that doesn't intersect, that doesn't cross this border, right? And for that reason, no matter how close to 1 I am, if I'm above it, I can always build an epsilon neighborhood that doesn't cross that border. Okay, and you could do something similar when P is less than 0. All right, so something similar can be done when P is less than 0. Right? It's the same argument, basically. But what about when P is in that interval 0 to 1? So if P is in 0 to 1, then what can we say? Well, it turns out if P is in the interval 0 to 1, then P is a limit point of E. Okay, so remember what E is. I'll rewrite it just because it's not on the page. E is equal to the intersection of the rational numbers and the interval 0 to 1, right? So this is sometimes when you see this, you may think like, oh, this is a sort of a small subset of the rational numbers. No, this is every rational number in 0 to 1. This is every rational number, the largest rational number being 1, the smallest one being 0 over whatever, so 0, and then everything in between. So like anything where the numerator is smaller than the denominator would be in this set of rational numbers. So 5 million over 5,000,001 is in this set. 136 over 248 is in this set, right? So every rational number between 0 and 1, every rational number where the numerator is smaller than the denominator is in this set, right? And so if you recall back to kind of the early lectures of the class, we had a theorem that said if x and y are real numbers, right? And if x is less than y, then there exists a rational number such that x is less than the rational number, which is less than y. So basically, for any two real numbers, there's a rational number between them. No matter how close x and y are, you're always going to be able to find a rational number to fit in between them. And so that's the basis for why everything in that interval must be a limit point. Okay, so if we assume that 0 is less than or equal to p, which is less than 1, then there's going to exist an r in q such that p is less than r, which is less than the minimum of p plus epsilon, comma 1, right? And that's the setup, right? So we can always find a rational number that is less than p plus epsilon and greater than p. All right, so there's always going to be a rational number that can be found. And then I'll leave it to you to see how to think about when p is equal to 1. It's similar. It's a similar idea. Okay, very good. Let's take a look at a theorem that leverages, or that is kind of about limit points. Okay, so we've got a theorem about limit points. So theorem, let's let E be a subset of R. Right, so I've got a subset of the real numbers E, and I've got two things to say about that. First of all, if P is a limit point of E, then every neighborhood of P is going to contain infinitely many points of E. Infinitely many points of E. Right, so this is another way to kind of characterize the idea of a limit point. Right, so if I've got a limit point, then no matter how small my epsilon neighborhood is, it's going to contain infinitely many points of E. So I think when we were first defining the idea of a limit point, we said, hey, I just need to be able to find for any epsilon greater than 0, there just needs to be another point of E in my epsilon neighborhood of P, and it can't be equal to P. But what this is saying is that, well, if you've got one point, you've got infinitely many. If you have a limit point, then no matter how, if you have a limit point, then no matter how small your epsilon neighborhood is, you're going to have infinitely many points in it. Okay, so if P is a limit point of E, then every epsilon neighborhood of P contains infinitely many points. So that's the first thing, and then the second part of this is that if P is a limit point of E, a limit point of E, then there exists a sequence P sub n equals 1 to infinity in E with the terms of that sequence not equal to P for all n in n, such that P sub n converges to P as n goes to infinity. Okay, right, so if I have a limit point of a set E, then I can construct a sequence in E that has my limit point as its limit. It's kind of part of where the idea of, part of where the term limit point comes from, right? So if I've got a limit point, then it's going to be the limit of some sequence for the set, right? And that one is a little harder to visualize. I think the first one, as amazing as it sounds when you say it, a little reflection makes it kind of seem clear. The second one is weirder, though. I think, when I remember going over this theorem initially when I was in undergrad, and I remember thinking, like, really? How do you do that? Let's walk through it. Let's go through the proof, and we'll see how both of these work. Okay, so for part A, there are different ways to prove it, but I think one of the best ways to see this is to do proof by contrapositive. Right, so we're going to do a proof of part A by contrapositive So if you recall if you've had a proofs course, or maybe you've seen this, the idea with a proof by contrapositive is that you assume the negation of the conclusion. So you assume the reverse of the conclusion, and then you use that to prove the reverse of the assumption, the hypothesis. Right? So my hypothesis is that if P is a limit point of E, and my conclusion is then every neighborhood of P contains infinitely many points. So by contrapositive, what I'm going to do is I'm going to start by assuming that there exists an epsilon neighborhood that doesn't contain infinitely many points, and I'm going to use that to show that my point P can't be a limit point. Okay, and so let's do this. So part A will say assume there exists, and I'm going to use a different notation. I'm going to use a delta. Assume there exists a delta greater than 0 such that the delta neighborhood of P actually contains only finitely many. It only contains finitely many points from E. And I'm going to actually name them. I'm going to say that set is Q1, Q2, ... up to Qm. Right? And then the assumption here is also that Qi is not equal to P. Okay. All right, so I'm assuming that I've found some distance from P which I can construct a neighborhood using, and within that neighborhood there's only finitely many points from E, right? So m of them, Q1 through Qm. Okay, and so then what I'm going to do is I'm going to say let's let epsilon equal the minimum of the distances between these points in the neighborhood and P. So it's the minimum of whatever P is minus Q1, and whatever P is minus whatever Q2 is, and so on. All right, I can do this. There's only finitely many of them. It might take a long time if there's a lot of them, but I can do it theoretically. P minus Q sub m. Right, so I've got the smallest distance between the finitely many points that are in my delta neighborhood. So I set epsilon equal to that. Then I've found an epsilon. I'll now have an epsilon greater than 0 such that the epsilon neighborhood of P intersecting E is equal to what? Well, the only thing in there is P, right? Because I've constructed my epsilon so that it excludes all of these. Okay. All right, and so if your epsilon neighborhood of P intersecting E is just P, then the implication is that P is not a limit point. Okay, so that's the proof for part A. Okay, and so the implication would be that the reverse would be true, right? If P is a limit point, then it has no neighborhoods with finitely many points. Right, so this implies that if P is a limit point, then it has no neighborhoods with finitely many points. Right, that's the part that we wanted to prove, and here we can see it. Okay, so that's part A. Let's take a look at part B now. Now remember, part B says, hey, look, I've got a set E and I've got a limit point in E, then I need to show that there's going to exist a sequence in E that converges to my limit point. Okay, so this will be the proof of B, right? So we wish to show that there exists P sub n where P sub n converges to P. Okay. And also that p sub n is not equal to p, right, for all n, right? So it's not just p repeated over and over again, right? So basically the idea here is we can just construct the sequence. We can construct the sequence. All right, how can we construct this? Now, since p is a limit point of E, here's how we construct it. So p is a limit point. P is a limit point of E, right? Then for each n in n, for each n natural number, right? For each n in n, by definition of the limit point, there exists a p sub n in E with p sub n not equal to p. Remember, this is the definition. And the distance between p sub n and the limit point p being less than 1 over n. Right? We could characterize it like this. Right? And so using this idea, we can build the sequence. We can choose p sub 1 minus p less than 1. P sub 2 minus p less than 1/2. And so on. Okay, we could build our sequence in this way. So Pn can be constructed. And obviously the way we're constructing this is obviously getting closer and closer to P. It's converging to P. Okay, so there you go. That's all there is to it. Right? We don't have to explicitly write the sequence. We just have to show that there is one. Okay. All right, very good. Very good. Okay, and kind of a quick corollary here before we go to the Bolzano-Weierstrass theorem is that, and this is something you probably have already thought of, a quick corollary here would be that a finite set has no limit points. I don't know what this is exactly a corollary of, but I suppose it's a corollary of the most recent theorem that, you know, where a part A of the most recent theorem where we said that if P is a limit point, then every neighborhood of P will contain infinitely many points. Well, if E is a finite set, then it's going to have no limit points, right? All right. So obviously, if you're a limit point, then if you're a limit point, you need to be able to, you must have infinitely many points in the epsilon, in any epsilon neighbor surrounding you. And so if the set under consideration is finite, then clearly it can't contain any limit points. Okay. All right, very good. I think I'm going to actually split this lecture into two videos, just to keep the length down. So we'll be right back with part B of this lecture, where we'll jump into the kind of the meat of, well, the main point, I would say, of this lecture, and that's the Bolzano-Weierstrass theorem. Okay, so we'll see you in a few.